This video is about the in-circuit programmer for the 6502 project. The concept behind this programmer is to be an in-circuit EEPROM programmer that will program the device on the CPU board. In a previous video, I explained in detail how the CPU board works, and at the heart of the decision-making or control logic is a part that's called a CPLD. The programmer is designed to work in conjunction with the CPLD. The software in the programmer will place the CPU board via the CPLD in all the different modes, depending on the functionality that we're trying to accomplish. The CPLD operates in three modes. Mode 1, standard mode, which is the default mode, where the CPU board acts like a computer. Mode 2 is EEPROM mode, where the programmer places the 6502 in a high-impedance state, and the programmer programs the EEPROM. Mode 3 is a hybrid mode. In this mode, the programmer is driving the 6502 clock, and between each clock cycle, the program monitors the address bus, data bus, and all the control lines, recording the steps that the 6502 is performing while it's executing code. This video is about the in-circuit programmer, theory of operation, and schematic review. At the heart of everything is the Microchip AVR64 DD32 microcontroller. I like this part a lot. It's very low cost and very flexible. It runs at 24 megahertz. It's got 64K of flash memory, 8K of RAM, and 256 bytes of EEPROM. But more on this part later. I will make a separate video on the AVR64 DD32 chip, the Microchip Studio, and the Atmel ICE or in-circuit pod. This programmer works in conjunction with a desktop application. The desktop application will communicate to the programmer via a USB interface. The USB interface is one of the FTDI chips. In the old days, a serial port was a 9-pin connector. For those who do not know, the FTDI chip is a chip that connects to the computer via USB interface, eliminating the need for the old 9-pin style connector. It's nothing more than a fancy, modern serial port with a USB connector. For the desktop software to communicate with the programmer, it simply opens up a COM or serial connection. The programmer itself is nothing more than a command line interpreter. What that means is the programmer has a list of commands programmed into the AVR chip that will perform specific tasks. The desktop software knows about these commands and sends them in a specific order for the programmer to perform a given function. As an example, the erase flash command. Coded within the programmer is an erase flash command. This command contains a sequence of steps, included how to set up the CPLD in the different modes, what control lines are needed, and what sequence or order they need to be programmed in order to program the EEPROM. The programming algorithm is stored in the AVR chip is specific to the part we are using. Since the programmer understands the steps necessary to erase the chip, the programmer will execute the command sequence, and when it's completed the request, it will return to the desktop a pass or failed message. Since there's a list of commands, the concept of sending a command between the desktop and the programmer will be the same. The difference is between each command. The response back to the desktop may not be a pass or fail. It might be a stream of data. More on this later. I will have two videos, one outlining the programming of the AVR chip and the other on the desktop software. Now back to the design review. The PC opens up a port via USB and sends and receives commands to the processor via the FTDI chip. So you'll notice that the FTDI has a transmit and receive, and the AVR chip also has a transmit and receive. So from the PC via USB to the FTDI, we end up getting to the AVR chip. Line drivers and buffers. There are two basic functionalities we need regarding addressing. The first one is to set the address bus so we can write to the EEPROM, and the other is to read the address bus when the 6502 is running in J-Link mode. U7 provides the hardware support for reading the address bus in J mode. In order to obtain the full address, the AVR needs to read U7 twice. The first read is the lower 8 bits A0 through A7 of the address, and the second read is the higher 8 bits A8 through A15 of the address. The AVR will then combine the two reads into a single address containing A0 through A15. The address will be stored in an internal memory location for use by the desktop later on. Setting up the address bus for programming the EEPROM takes the combination of B1, B2, and U1. The AVR loads the address portion A0 to A7 into B1, and then loads A8 to A15 into B2. B1 and B2 are latch registers. A latch register stores data until it can be used at a later time. The AVR will then lower BOE, which will place the latched address information on the address bus. This would be part of the sequence to read or write to either RAM or EEPROM memory locations. The CPU board interface. At the bottom of the programmer are connectors J2 through J6. This contains all the address information data as well as control lines to talk to the CPU board. Also pictured here is J4, which is labeled TLA clock. I have a logic analyzer, a TLA 5202. I will use this to capture a sequence of events. I like to drive the TLA with a synchronous clock. That way the captures are more accurate. In all my designs, I've added in this poor man's logic analyzer, which is a series of LEDs that will show the active state of any of the pins. In this case, it's the address lines, the data lines, and control lines. An active state is when the LED is turned on because the state of which the pin it's connected to is active. That doesn't always mean it's active high or active low. It means the active state for the device it's talking to. So if the active state of a line is high, there's an inverter so that there is a place to sync the current through the LED. If it's active low, then there's no need to have a path to ground because the low state will allow the LED to illuminate. The next page of the schematic is the power supply. I see that I made an error here. I normally like to use a 3-wire connector with the center position being powered and the two outer pins being ground. That way it doesn't matter if you plug in the connector backwards. I apparently missed this in design review, so add that to your notes when you're doing designs to make sure you've accomplished all the goals that you're looking for. I did, however, add D1, which is a protection diode. In the event that you plug in the power supply backwards, it won't harm the board. Either way, it doesn't really matter on this board because I'm going to be powering it by the USB connector. So I guess this is probably a moot point, but you still want to have a checklist when you're doing your design.